Good morning, my dear students. Today we will discuss some problems based on kinetic theory in physics. Kinetic theory of gases, class 11, physics. The kinetic theory was developed in the 19th century by Maxwell and Boltzmann and others. It explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms or molecules. So, for any body, when it is moving, that arises the kinetics, the kinetic energy. See, the molecules are collided each other and thereby pressure is exerted. Let us consider a container where you got various gaseous molecules. We know the intermolecular force of attraction is the least in the case of gas. However, let us consider the center molecule that is pulled equally in all directions. But another molecule which is about to collide with the wall of the container, there is a counter force for the upward by the downward. But there is no left force to compensate the right force. And there arises the motion. And the molecules hence they are moving here and there, they can collide themselves among themselves, and they can collide on the wall also, thereby pressure is exerted. We know, according to Boyle's law, the volume of given mass of a gas is inversely proportional to pressure at constant temperature. We can introduce a constant when we remove the proportionality. So we can call it V is equal to a constant divided by P. It means PV is equal to constant. So this equation can be written as P1 V1 is equal to P2 V2, that represent the different conditions of pressure and volume. Likewise, it can go on P3 V3, P4 V4, etc. So the Boyle's law can be represented by this equation also. One is this one, another is this one. Now we can bring this P2 here. So P1 by P2 is equal to V2 by V1. So like this also we can represent. According to Charles' law, V is proportional to temperature at constant pressure. Charles' law 2 states that pressure is directly proportional to temperature at constant volume. So we can bring everything together so that we are able to get PV is proportional to constant. So let us introduce a constant here. This is called gas constant. And if there are n number of moles, we can say PV is equal to nRT, and this is called equation of state for ideal gas, or you can call it ideal gas equation or perfect gas equation. Now, the molecule of an ideal gas is a point mass. It has no geometrical dimension. And when we consider the kinetic theory and gas pressure, we need to consider P is equal to this equation 1 by 3 rho C squared bar. This represents the C squared bar is nothing but mean square velocity of the gas molecules. Mean square means that is C1 squared because it consists of n number of molecules, So each molecule will be traveling at different speed means that can be represented by C1, C2, C3. And we need to consider all. Let us consider the mean square velocity. What do you understand from this? C1 squared plus C2 squared plus C3 squared plus etc. divided by n number of molecules. So this can be represented as C squared bar, right? So that is why we represent this as what? That is mean square velocity of the molecules, gaseous molecules. Rho is density, density of the gas. Rho is density. Therefore, rho is equal to mass by volume. That we know. Is it not? Mass by volume is equal to density. And if it consists of n number of molecules, you can put nm divided by volume. That is total mass of the gas divided by volume. Therefore, instead of rho, we can put this nm divided by v. Therefore, P is equal to 1 by 3 n m divided by v into c squared bar. So this is the expanded equation where v is the volume of the container, n number of moles of gas, m mass of each gas molecule, nm the total mass, p the pressure, right? Okay. Then let us consider the Gay-Lussac's law or the pressure law also. Charles' law stated V is proportional to T. It means V by T is equal to constant according to Charles' law. Charles' law. And according to Gay-Lussac's law. Gay-Lussac law. It is also called the pressure law. So this is represented as P is proportional to T. Therefore, P by T is equal to constant. So these two equations can be represented by, in fact, this is represented by P1 by T1 is equal to P2 by T2. Similarly, the Charles law can be represented by V1 by T1 is equal to V2 by T2. Now, as we have already derived from these equations of the ideal gas equation, that is a PV is equal to nRT, where R is the gas constant, universal gas constant, universal gas constant. Therefore, and you should know the value of R also. That is, R is given as is a constant, so 8.315 joule Kelvin per Kelvin per mole. In fact, we can derive this value by rearranging this equation. We know already PV is equal to nRT. Therefore, nRT we let us rewrite like this. nRT is equal to PV. R is equal to PV by nRT. Right? So, the pressure that is 1 atmosphere. Volume 22.4 liters. That is, pressure is equal to 1 atmosphere. And volume is, that is 22.4 liter at STP. And N number of moles. Let us say 1 mole. And T temperature in Kelvin. So in that case, by substituting the values, you are able to get R is equal to 8.315 joule per Kelvin per mole. Avogadro's law. Avogadro's law states that Avogadro states that equal volume of all gases under standard temperature pressure contain the same number of molecules, and they are 6.023 into 10 power 23. Graham's law. And Avogadro's volume is supposed to be 22.4 liter per mole, molar volume, you can say. And 1 liter is equal to, that is 10 power minus 3 cubic meter. So this is also represented as 22.4 into 10 power minus 3 cubic meter. It means 2.24 into 10 power minus 2 cubic meter. Some authors, they represent the liter by cubic decimeter, because 1 liter is equal to 1 cubic decimeter. So you can mention this as 22.4 liter, 22.4 decimeter cube also. So this is the Avogadro's volume. Whenever you say Avogadro's volume, it should be per mole. If it is Avogadro's number, per mole, that is 6.023 into 10 power 23. Graham's law of diffusion. Graham's law of diffusion. It states that the rate of diffusion, what do you mean by diffusion? The spreading tendency. If it is a solid, it won't spread here and there. If it is a liquid, it will be moving. If it is a gas, it will be moving much faster because the rate of diffusion is more. So, the rate of diffusion, that is represented by R, is proportional to the whole square root of L by rho. 1 by rho, not L, 1 by rho. It means denser the gas, slower is the rate of diffusion. Denser the gas, slower is the rate of diffusion. Then Dalton's law of partial pressure. Dalton's law of partial pressure. It states that the resultant pressure exerted by a mixture of non-interacting gases is equal to the sum of their individual pressures. Let me consider I have two compartments, and in between that, this separator can be removed at any time. So previously there was a gas with the pressure P1. In another chamber, you got the gas with pressure P2. Now let me lift this partition. So it becomes what? That is, I lifted now P1 plus P2. This is the total pressure. So P is equal to P1 plus P2. And these individual pressures are called partial pressure. So the pressure of the mixer is equal to the sum of individual pressures, that is, sum of pressures of individual gases. So it can be P is equal to P1 plus P2 if it is having n number of molecules or n number of gases. with the different pressures. So you can put and so on. This is called the Dalton's law of partial pressure. Then, mean or average speed of molecules. Mean or average speed of molecules or mean velocity of molecules. It is given by V mean velocity is equal to V1 plus V2 because it consists of n number of molecules, is it not? So, and so on up to Vn whole divided by n number of molecules. So, this is called mean speed, and it is given by, that is, this V mean is given by the whole square root of 8 kb. Kb is the Boltzmann constant into temperature in absolute scale, that is in Kelvin, pi into mass divided by pi into mass. Here m is the mass of one molecule and temperature, that is represented by T, that is the temperature of the gas. And we have another term called VRMS, that is root mean square velocity. It means we have got square velocity, mean square velocity, that is V1 squared, V2 squared, V3 squared, etc. up to Vn squared and divided by n number of molecules. This is called mean square velocity. And let us put the square root of this. This is called VRMS, that is root mean square velocity. So this VRMS is given by 3p by rho. Rho is nothing but mass by volume. So that is given as the whole square root of 3 into Boltzmann constant into temperature divided by mass of the gaseous molecule, one molecule. Okay, right. And based on which we can arrive at the most probable velocity. It is the speed which is possessed by maximum number of molecules, that is called most probable velocity. It can be represented by Vmp, that is equal to the whole square root of 2 kb Bose constant into T whole divided by m, where T temperature, kb Boltzmann constant, m mass of a molecule, gaseous molecule. Now let us talk about the kinetic interpretation of temperature. Kinetic interpretation of temperature. Let us consider the kinetic energy as U. This is given by 3 by 2 of R into T. Okay. So here the temperature of the gas, that is T, and the average kinetic energy. This is the average kinetic energy of the molecules of the gas. So according to this interpretation, the average kinetic energy is zero when T is equal to zero. So U becomes zero at absolute scale, that is when T is equal to 0 Kelvin, right? So the motion of the molecules ceases together at absolute zero. There is no movement at all. It is static. Then degree of freedom. Degrees of freedom. This is another important concept. The total number of independent coordinates required to specify the position of the molecule. or the number of independent modes of motion possible with any molecule. This is called degree of freedom. So, what is degree of freedom? The total number of independent total number of independent coordinates mean was xyz required for what? To specify the position, to specify the position of a molecule, of a molecule. So this is known as degree of freedom, degrees of freedom. And this can have monoatomic, diatomic, triatomic, or polyatomic. So this type of molecules can have, that is, if it is a mono, it has got the degree of freedom 3. If it is a di, it has got the degree of freedom 5. And if it has a n number of molecules, that is polyatomic, then you can put 3n minus k number of degrees of freedom. So these are all degrees of freedom. So where k represents the restriction, the number of constraints, you can say the constraints or restrictions associated with the structure. So that is called k, right? Then law of equipartition of energy. Law of equipartition of energy. This law of equipartition of energy is nothing but this is applicable for a dynamic system in thermal equilibrium. Is applicable for dynamic system in equilibrium. The energy of the system is distributed equally. The energy is distributed. The energy is distributed equally. The energy is distributed equally among the various degrees of among various degrees of freedom. And we can also call it the energy associated with each degree of freedom per molecule as, that is, energy associated with each degree of freedom. Each degree of freedom per molecule. Per molecule is represented as 1 by k into T, where k is the Boltzmann constant. First of all, you should understand the degree of freedom. Let me say this is x-axis, this is y-axis, this is z-axis. Let me keep a monoatomic molecule at the center. So the monoatomic molecule can move towards x-axis, it can move towards y-axis, it can move towards z-axis three-dimensionally. So that is why we call the degree of freedom for a monoatomic gaseous molecule is 3. So for the energy associated with each degree of freedom per molecule, that is given as 1 by 2 into kT, where K is the Boltzmann constant, T is the temperature in Kelvin. Next, mean free path. Mean free path. Mean free path of a molecule in a gas is the average distance traveled by the molecule, traveled by the molecule between two successive collisions, between two successive collision. We already discussed the pressure is exerted by the collision of molecules among themselves and with wall of the container. So let me consider a molecule 1, molecule 2. It is going to collide with each other. So what is the average distance traveled by these molecules to have this collision successively next to next? Then, so it can collide like this, and again it can collide with another molecule. So what is the average distance? Okay, and this is the mean free path. Let me say lambda 1. So this molecule will be traveling with the distance lambda 1, and this is lambda 2, and this is lambda 3, etc. So let me consider it consists of n number of molecules. So in that case, the mean free path traveled by the molecules lambda 1 plus lambda 2 plus lambda 3, etc., up to lambda n whole divided by the n, the total number of molecules, not molecules, successive collisions. So n is the total number of successive collision. Successive collisions. Okay. So this is given by the modulus of 1 by the whole square root of 2 pi d squared into n. That is given as modulus of kt divided by the whole square root of 2 pi d squared into rho, where d is the, let me consider this molecule, and this is the diameter of the molecule. So this is d, diameter of the molecule. And n, the number of molecules per unit volume. N is equal to number of molecules per unit volume. T, absolute temperature. P, pressure. So from this we can find the following, we can give the following statements. For example, let me consider this. The number of molecules per unit volume, that is represented as n, is it not? So, is smaller, okay, then what will happen? The lambda is larger because it is inversely proportional, okay. So, let us give the statements based on this equation. Statement 1, that is, smaller the number of molecules, greater will be the mean free path. Okay. Second statement, smaller the diameter. So the diameter is smaller. Definitely larger will be the mean free path. Third, smaller the density. and then larger will be the mean free path. So in the case of vacuum, in case of vacuum, in vacuum, VUCUUM, vacuum, rho is equal to 0. So it means the lambda becomes infinity. Okay, that is mean free path becomes infinity. And fourth statement, smaller the pressure, when the pressure is less, then larger will be the mean free path. When the temperature is less, then larger will be the mean free path. So all these statements are given based on these two equations. Okay, so not smaller because it is in the numerator. So larger the temperature, larger will be the mean free path. Okay, right. Then, and we should be aware of a certain that is important tables also. For example, we should know what is a CP, what is a CV, and let me say heat capacity. Heat capacity. The heat capacity is the that is it is a temperature required. For example, there are two important terms: specific heat capacity, or you can call it molar specific heat capacity. And this is molar specific heat capacity at constant volume. This is molar specific capacity at constant pressure. So it is the quantity of heat required to raise the temperature by 1 degree for a given amount of molecule, or if it is a mole means if it is it can be given as mole, then to raise the temperature by 1 degree, okay, at constant pressure. So it is a quantity of heat. What is the specific heat? Quantity of heat. This is heat capacity. Heat capacity. Quantity of heat required by a given amount of a substance, in this case gas. So quantity of heat required by a given amount of gas to raise the temperature by 1 degree or 1 Kelvin. When it is at constant pressure per mole, instead of given amount, you can put per mole, then it becomes Cp. Cv is molar specific heat capacity at constant volume. That is at constant volume. That's all. Okay. So there is an equation called Mayer's equation. Equation is given by Cp minus Cv is equal to R. And you should be aware of the that is Cv or Cp. The unit is joule per mole per Kelvin. Okay. Now let us discuss about some of the important problems in this topic. Let us discuss the first problem. Take down. Estimate the fraction. Estimate the fraction of molecular volume. Volume to the actual volume. Occupied by oxygen gas at STP standard temperature pressure. The diameter of oxygen molecule is 3 Armstrong. Now, for any problems in physics, you should adopt the concept called kudos. That is, K stands for known, U stands for unknown, D definition, O output, S substantiation, means justification. So, first of all, you should be able to extract the data, that is the given data. So, you can call it the given data. And you had to find out. So, to find D, that is nothing but the formula, the required formula or theorem or equation. O, you had to substitute and get it. You had to rearrange, and based on that now, you had to find out. Substitute the values. Substantiation means you have to justify your answer, justification with the appropriate unit. So, all these steps should be very, very clear when we solve any problems, whether it is physics or chemistry or mathematics. Now, estimate the fraction of molecular volume to actual volume. It means that is V actual divided by V molar is asked. This is to find out. And what are given here? The diameter is given. What is the diameter? So this is to find and given the diameter. It is given in 3 Armstrong unit. 1 Armstrong is equal to 10 power minus 10 meter. So you have to put 3 into 10 power minus 10 meter. You had to convert the unit suitably so that you can insert in the required equation. And that is why you have to be very careful about the unit conversion. And then, according to Avogadro's number, see, whenever we talk about the data, there are some data given directly. Let me consider the data given in the or found in the statement or the problem. There are 3 types of data. One is direct data. Second is the reference data. Third is the derived data. You had to derive some data suitably. So here you need some of the references also. Avogadro's number, because it is talking about the molar volume. So we should be aware of Avogadro's number. Avogadro's number is nothing but 6.023 into 10 power 23. And it means what? When we take 1 mole of oxygen molecule, it consists of 6.023 into 10 power 23 molecules. So you have to say per mole. Actually, Avogadro's number is something like that is when you say that is 1 dozen means 1 dozen apple means 12 apples. Is that not? So similarly, when I say 1 mole of any gas molecule means that 6.023 into 10 power 23 number of gaseous molecules, in this case oxygen. So V actual means that is the volume occupied by the gas, that is actual volume, is given by you got a small volume into total number of gas, is it not? So it should be what? The volume is given by, let us consider the molecule as a sphere. So volume of the sphere is equal to 4 by 3 pi r cube. Are you able to follow? So you have to consider this actual volume as, that is, V into Avogadro's number. So therefore, we have to multiply, that is Avogadro's number, with 4 by 3 pi r cube into Avogadro's number. Okay. So, you know, diameter is 2r. Therefore, r is equal to d by 2. Are you able to follow? So you have to substitute accordingly. So let us calculate the actual volume, 4 by 3 pi into d by 2 whole cube into Avogadro's number. So this is the equation where we have to substitute the given parameters. So that is equal to 4 by 3 into, and pi 3.14 into d. D is given as a 3 here, is it not? So 3 by 2 whole cube, diameter divided by 2, that is the radius, into, and in fact you have got the meter, is it not? So this is given as, you have to be very careful, 3 into 10 power minus 10. So 3 into, let us put like this, 3 by 2 into 10 power minus 10 whole cube. Okay, right. And then into 6.02 into 10 power 23 cubic meter. Are you able to follow? So when we solve all these things, you can use the calculator or the logarithm table. You are able to get the answer 8.51 into 10 power minus 6 cubic meter. See, 1 cubic meter is equal to, otherwise 1 liter is equal to 10 power minus 3 cubic meter. That is 1 kiloliter is equal to 1 cubic meter. 1 kiloliter means 10 cube liter is equal to 1 cubic meter. Therefore, 1 liter is equal to 1 by 10 cubic meter. That is why 1 liter is equal to 10 power minus 3 cubic meter. Similarly, you should know 1 decimeter cube is equal to 1 liter. And you should also know 10 cube centimeter cube is equal to 1 liter. It means 1000 cubic centimeter is equal to 1 liter. It means 1000 ml is equal to 1 liter. So you should be aware of all these conversions, unit conversions. Now let us take this one. 1 liter is equal to 10 power minus 3 cubic meter. Let us substitute. Therefore, 8.51 into, we are able to get 10 power minus 3 liter. I have converted this. Okay. So the volume of the molecule, that is actual volume, is given as how much? 8.51 into 10 power minus 3 liter. What is the molar volume? The molar volume is, that is 22.4 liter. That is Avogadro's volume. Molar volume 22.4 liter at the STP. Now what is asked here? The V actual divided by V molar. So that is given as, that is 8.51 into 10 power minus 3 divided by 22.4 liter. Okay. Now we are able to get 3.8 into 10 power minus 4. Roughly 4 into 10 power minus 4. It doesn't have unit because it is only a fraction. Okay. So let us continue this class in the subsequent days. If there is any doubt, you can ask in the comments column or in our Telegram system. Thank you.